My favorite part's the I didn't get that one. Wait, what did I have? Nosebleeds or the hot section?
Boyle's Law. Shh, please listen. Okay. So, and Boyle also lived in London. Okay. Boyle.
Do we need to know that?
No.
What's his name?
How you spell it?
B-O-Y-L-E and then apostrophe S. Lower it? Like closer? Well, if I do that, then you can't see the whole page. Now what you want? How about that? Better? You like that? Okay. Boyle's Law. When Boyle was studying pressure and volume, he found that there is a direct relationship, there's an indirect relationship between pressure and volume, such that if you have a fixed amount of gas in a container, and and let's say the container can vary its volume, okay, so you can you can change the pressure and change the volume, all right, but he's not changing the temperature, just the pressure and volume. He found that if pressure is increased, the volume will respond by decreasing. Peak for pressure. Correct. Peak for pressure. Okay? And the mathematical relationship is really, really straightforward. What he found was that if you multiply pressure times volume, we get a constant. Pressure times volume, we get a constant. Now yesterday when we were looking at Charles' Law, we found that V over T gave us a straight line. Well, this is not a fraction. This is multiplication. Okay? So we don't get a straight line from this. Now K is still a slope, but it's a slope that changes. Okay? The slope is never the same in two different places. If you have a direct or an indirect relationship like this where one thing goes up while the other one goes down, and you graph it, you don't get a straight line. An indirect relationship gives you a graph that looks like this. Gives you a graph that looks like that. Indirect. Now, there are two kinds of graphs that you need to know in a science class. There are lots of patterns that can be described with a word or two, okay? Indirect. There are logarithmic patterns, all kinds of patterns when you graph things. But the two that at this point in time, at this level, high school level, you're supposed to know when you see are an indirect pattern. So if you see a graph where the data makes this kind of curve, you should know automatically that's an indirect relationship between two variables. Got that?
Got that.
Okay. And yesterday when we showed that straight line graph with a positive slope, when you see something like that, you should know automatically that is a direct relationship. Okay? You can also call this an inverse relationship. In fact, it's probably called an inverse relationship more often. Okay? So let's call this inverse. You need to know when you see this, it's an inverse relationship. And just for what we said yesterday, I'll just put it down in the bottom right-hand corner. When you get a graph that looks like this, direct relationship. That means the variables change in a direct way, and up here, the variables change in an inverse way. Okay? That's what we did yesterday. That was one yesterday. You just need to know that's direct. Okay? You know this is inverse. Okay? All right, so now solving the problem, this is a gas law problem. We're going to solve it exactly the same way we do with Charles' Law. In fact, this is probably easier to solve because we don't have to do any conversions to Kelvin temperature. Okay? We just solved it all exactly the same way. We're going to set up the equation, plug in the value. Well, first thing we're going to do is write a list of knowns and unknowns, then find the equation that fits that set of knowns and unknowns. We're going to isolate the unknown and solve the problem around. Okay? Same set of steps. All right? So let's come up with a problem then. Here's our practice problem then. Hmm? Yeah, example. Okay, sure. So our example is if a gas is contained in a cylinder with a movable piston and the gas initially has a volume, since I lowered this, we must adjust the focus here a bit, initially has a, let's say, a volume, we're getting off the screen, of 12.5 milliliters, volume of 12.5 milliliters, under a pressure of 2.25 small letters ATM. That stands for something called atmosphere, or atmospheres. Okay. I'm trying to put it on here so you can see everything. Because somebody wanted me to lower the camera down lower. What would the pressure be? All right, I'll read the problem out to you while you're writing it down. All right? So if a gas is contained in a cylinder with a movable piston, and the gas initially has a volume of 12.5 milliliters under a pressure of 2.25 atmospheres, and the volume is increased to 19.3 milliliters, what would the pressure be? I left off one word there.
Question mark.
Yes, I got to also take out this period here. That's what I'm working on right now. Question mark. All right. So you now know how to make a list of knowns and unknowns. Please make a list of knowns and unknowns. Please make a list of knowns and unknowns. We'll practice that first. Okay? So it says the gas initially has a volume of 12.5 milliliters. So that tells you right there, that's what? V equals 12.5. And it says it has a pressure, well that's her clue, that's P, right? 2.25 atmospheres. Alright? And the volume was increased, so that must be a second volume. Making that the initial volume, volume 1. It's increased to 19.3 milliliters. What would the pressure be? So that must be pressure 2 to go along with it. It probably helps a lot if you're watching and listening up here. Okay? Alright. Now, just like with Charles' law, if I initially have a pressure, and whatever the pressure and volume are, they're going to equal some constant. So if I change the pressure, the volume has to change so we are still are equal in K. So if this is P1 and V1, this makes this P2 and V2, which means then that P1 times V1 equals P2 times V2. And that's the most practical form of the equation to use for solving these problems. And in fact, if you look V1, P1, V2, P2, you look for an equation on your list of equations here in your test references, there's P1, V1 equals P2, V2.
So that's how to write it, after we do unknowns.
Then after you write your list of knowns and unknowns here, then you just find the equation that fits that list. Okay? All right, so we want to have P1, V1 equals P2, V2. And then what's the next step? Plug it in. What is that commercial? There you go. That's it. All right. So we're going to, P1 is 2.25 atmospheres. And V1 is 12.5 milliliters. And P2 we don't know. And V2 is 19.3 milliliters. So we need to isolate the unknown. That's our next step. How do we isolate P2? Get it all by itself. Divide now. There you go. What do we divide by? And if I divide this side by 19.3, I must divide the other side by the same thing. Now I can simplify a little bit. What do I need to do to simplify? 19.3 goes away. How about on this side? Can I simplify anything? Milliliters. And what I have now are units of atmospheres. And we already set up here atmospheres measure pressure. So I know I probably set it up properly. Okay? I'm just ready to do the math. So 2.25 times 12.5. Going to remember you have to hit enter first, then divide by 19.3. Now some calculators will give you the right answer anyway, and some won't. But everybody's calculator will give you the right answer if you do these steps in this way. Okay. So it's a way of making sure everybody's getting the right thing without having to. Okay, sorry. Yours may have a few less numbers on the end. Well, okay. What units of measurement do I need to move down here? ATM. And that equals the P2. And we need to underline any insignificant digits. Do we have any? Well, we have 3 significant digits, so we got a bunch of insignificant digits. 1, 2, 3 significant digits, because all these numbers have 3 digits up here. All of our measured numbers have 3 digits, so our final answer needs to have 3. Starting here, we underline then. All the insignificant digits get underlined. We're going to draw an arrow. And we're going to round that off to 1.46 atmospheres equals P2. It's a pressure unit. It's like when you go and fill up your tire with air, you use what's called pounds per square inch, or PSI, right? Well, this is a different pressure unit, and it's one that's used, in weather a lot, because atmospheres is what 1 atmosphere is the average pressure of air at sea level.